Hello. So this is the continuation of the web series on testing strategies for the ACS organic chemistry exam. So again, these are testing strategies for that exam, but that can also be applied for when you take the MCAT, DAT, GRE, etc. Again, we don't always have to solve the answer or solve the complete structures and things like that, but being able to, we may be able to just knock out what it can be quite quickly. So for here, so on to stereoisomers, we're going to look at, there's almost always a question about meso compounds. Okay, so meso means that you do have a chiral center, at least one chiral center, usually it's two, or more, but you have a plane of symmetry in here, so that so the mirror image within the molecule is the same. So for this one here, right, so you could have a plane of symmetry here, right? So you've got hydrogens below. So this side of the molecule, right? So the methyls would be on the same side, right? So that would be a nice mirror plane of symmetry that goes through here. So this one's going to be meso. Here, this one's not, okay? Because if you tried to put your plane of symmetry here, right, the mirror right there, you'd have going up out of the page, you'd have a methyl group, and on the other side would be a hydrogen. So it can't be this one. Here, this is sort of a classic one. Well, here, let's go down here, right? So on here you've got methyl and chlorine. So there's no way, right? If you try to do a plane of symmetry, right, they're not even the same things. So it can't definitely be that one. Here, this one's one of the ones that they try to trick you up on. I've seen this before, where you say, oh, there's a nice plane of symmetry going right here, right? Because you can slice through an atom. That's not a big deal. The problem is there actually aren't any chiral centers in this molecule, right? Because remember, for chiral center, you need to have 4 different things hanging off of it, right? So if we're looking here, you look at chlorine, hydrogen, right? CH2, CH2, right? So this would be it'd be a tie. Okay, so what you do with the ties, you keep going, right? So instead of doing that, now we're going here, and obviously that's the same because it's the same point. So then you compare, these two. If those are the same, you keep going until either one of two things: either you find a difference, or you get to the end of your chain, or you get to the all the way around the cyclic compound. And for here, it'd be the same with this one, right? So we get a hydrogen, right? So for right there, you have a CH3H, CH2, CH2. So you skip out here, right there. And so in fact, this one doesn't have any chiral centers in it, so it can't be meso. Okay, so be careful with that. Okay, so for Newman projections, right, we're going to be looking straight down the bond. Okay, so that represent the most stable configuration. So the first thing we got to do is to make sure that the molecules themselves are this configuration. Okay? So one of the things you can do is to go in and draw this out as like what's this? Draw this out as a skeletal structure if this is easier for you to see. So we have a CH2, right, CH2, and then this one has an H, so CH3 like that. This side here is a CH2, so H, and then it has the CH3 like that. So sometimes if you draw it out like this, outside of this condensed structure, sometimes it's a little bit easier to see. What we're going to be looking at is this, these carbon atoms here. And so it doesn't technically matter which way you look at it, but if you look at the molecule, the way it's drawn, so this front circle is this carbon here. This carbon here is behind, so it's obscured. Okay, so this carbon here is that one there. Okay? Is that one there. And so what does it have hanging off? It's got a hydrogen and 2 methyls. Hydrogen, 2 methyls. The carbon behind is obscured, right? So if you're looking at this, right, you can't see the tip, right, because it's obscured, but you know that it's there. And hanging off of it, right, would be 2 hydrogens, right, here and here, and this methyl group. Okay, so we need, say, two methyl groups in a hydrogen, 2 hydrogens and a methyl in the back. Okay, Okay, so here so this is okay. This one here, this one's okay. Two hydrogens, two methyls and a hydrogen, two hydrogens and a methyl. And this one's bad. Here, notice how there's 3 methyl groups on the front on 1 carbon. That's not what we have. Right? So this would be the most stable of all of them. This is not that molecule, so we can knock this out. The other thing is, if you have this is an eclipsed version. Eclipse is almost never going to be the most stable. So we don't even have to worry about that. We just knock it out. Right? So for this one, what we're looking for is we're looking for Gaussian interactions, which are these interactions here. Okay. Now, you're not going to get a Gaussian interaction from something in a hydrogen. Hydrogens are too small. But for here, we have a methyl-methyl gauche here. We have a methyl-methyl gauche here. We're trying to minimize those. And so for here, you've got 2 of them. Here it's CH, but we have 1 right here. So we only have the 1 here, but we have 2. So this is going to be the most stable. First thing to do is to knock out any molecules that are not this configuration. Right? So for here, the other thing is if you're looking at most stable, it's not going to be eclipsed. So you can knock that out. So now we're just down to these 2. Okay? So then you can get into the nitty-gritty. Okay, so for here, the Fisher projection. Okay, so for this one, there's a couple of different things. And 2, 3, 2, 3. The R and the S. This one you kind of have to brute force it. But the first thing you have to do is make sure you know which one's 1, 2, 3, and 4, right? So 2S. So this is in carbon 2. It's would be here, and then carbon 3 here, right? Because we've got this is a carboxylic acid, right? So that it's that functional group. Okay, that's going to be the highest priority for all of these because it's got this carbon has 3 CO bonds and these only have 1. Okay, so this is going to be 1, 2, 3, 4. So we have to make sure we know which one's 2 and which one's 3. Okay, so for moving forward, what you're going to have to do is then have to remember how Fisher projections work. Okay, they're sort of like bow ties. Okay, and so anything horizontal is going to be a wedge. Okay, and so this carbon here, right, we only have 3 bonds, right? So that means that there must be hydrogen over here. And then anything vertical is a dash. Okay, so again, we're going to have H, vertical, and then dash. Okay? So we're going to have to take these one at a time. Okay? So for this one, let's do this in blue. So remember, we have to do the priority groups. Okay? So for here, we have carbon, oxygen, carbon, hydrogen. Okay, so this OH is going to be number 1, okay, because of that oxygen. These carbons we don't know yet, and then this one is going to be number 4. We do know that's going to be number 4. Okay? So for here, we've got for this one we need to look at the bonds. Okay, this one has 3 CO bonds. Okay, 1, 2, 3, and then this carbon-carbon bond here. We don't worry about this OH bond because that's not hanging off. We're just interested in the 4 bonds of that carbon that's immediately next to here. So for here we've got 2 carbon-carbon bonds, right? 1, right? So, I'm sorry. We're just looking at this one. Oh yeah, no, it's good. We're looking at this carbon, right? So it's got 2 carbon-carbon bonds, right? 1, 2. 1 CO bond right there, and 1 CH bond. Okay, so you're looking at the heaviest bond, and so for here it's a CO versus CO. This one has 3. That's a tie. Okay, so then you look at how many there are. This one has 3 of them. This one has 1. Okay, so if this was like a carbon-chlorine bond, even though it would be 1, it would be the higher priority. So this ends up being the higher priority here, right? So this ends up being 2, 2, and then 3. Okay, so what I would do at this stage is to just draw. I like to draw these out just with the numbers, so it ends up being 4, 1, 2, 3. Okay, so get rid of all this chicken scratch over here. Okay, so if you can bring to your exam a model kit, even if it's just this, that works really, really well. I'll show you some strategies how to do this if you don't. So here we go. So if this is 1, 2, 3, let's see, 1, 2, 3, 4. Okay, if you're going to do the steering wheel method, you need to rotate this back. And so this ends up rotating to, right? So we're going to slide this over here, so it ends up being 1, 2, 3, and then 4 going behind. Right? So I just took this, rotated that back. Okay? And so since you're going like this, right, you're going clockwise, so that ends up being 1. Okay? So don't forget clockwise, counterclockwise. The 4 has to be going away if you're doing this with the steering wheel method. It has to go away. Okay, the other way that you can do it, okay, is with your hand, and this works pretty well if you can't bring a monitor. You could visualize it moving over. That's sometimes hard for students to do. Sometimes hard for me to do. Something like that. And so the way that I was taught is to say, okay, let's say let's point your thumb towards 4. So 4 is going that way, so we have to go like this. Okay. Now it's going to be. You can always turn. Don't forget you can turn your paper when you do this. So you start your fingertips at 1. Okay, so it'd be like this, and then you curl them around. So 1, 2, 3. Okay, so 1, 2, and then 3 like this, with your thumb pointing wherever 4 is. Okay, so it's like this. So 1, 2, 3. Right. Since I'm curling with my right hand, it's R. Because if I try to do this, so 4, sort of point it there, so the 1 is out here. Right? If I try to go 2, right, I'm going to break my fingers. Right? But if I try it like this, 1, 2, like this, 1, 2, like that, I'm curling with my right hand. So that's the way. So the nice thing is you don't have, once you get to this one, you can just rotate your wrist wherever 4 is. That's where your thumb is going to be pointing, and then you try to rotate from 1, 2, 3. So like that. If you can get to 1, 2, you're fine. Heck, if you can go 2, 3, you're fine. Don't forget, you can rotate. You can move your paper around. Now you can't pick it up like and show it everybody, but you can rotate it around. So now we know that 2 is going to be the R, right? So we can get rid of these 2. So if you're like, oh, I need to move on, you now have a 50-50 chance. So let's go ahead and solve this one. Okay, so now this one you have to completely reset everything. Okay. So for here, right? So now we're looking at oxygen, carbon, hydrogen, carbon. Okay, so this is going to be number 1. This is going to be number 4. Carbon, carbon. So now we need to look at this versus that. Okay, and so for here we have 1 carbon-carbon bond, 1 CO bond, okay, and 2 CH bonds, right? Because there's only 2 bonds shown, so the other 2 is CHs. Here we've got we have 2 carbon-carbon bonds, right? 1 CO bond, okay, and then 1 CH. Okay, so CO versus CO, okay, right? That's a tie. But notice how this one has 2 carbon-carbon bonds. Versus 2 carbon-carbons. That makes this to be a slightly higher priority than this one. Okay? And so it ends up working out that, again, we're going to do 1, 4, 2, 3. And notice you could just go, hey, notice how these 2 are held fixed, and we flip these 2? Well, then it better be S. You could do that. And you could just say, yep, that's S, move on. Okay. If you want, again, if you wanted to completely solve this, just to get for practice, on your own, if you want to practice this, again, you have to rotate this around, so it ends up being no, that is 2, 3. So now this is 2. Right, so 1, 2, 3. Right, so we're going to rotate it. This is going to be S. The other thing, again, you could just notice, oh look, I just flipped those 2. Again, if you're going to do the hand method, right, your thumb is going to be pointed that way. 1 is up here at your fingertips, and 1, 2, 1, 2. So since you're going with your right hand, that would be S. So it's RS. So that one there. Again, this is a little bit, sometimes you just kind of got to brute force it through. Okay, so relationship between these two molecules. Okay, so when you have something like this, enantiomers mean that you've switched all wedges and dashes. For diastereomers, it's not all. Okay, not all. So if you only have one chiral center, right, and you've switched the wedge and dash, you've switched them all, right? So they're enantiomers. But if you have two of them, if you only switch one, then they're diastereomers. So for here, notice how we've kept this one fixed, but we've changed this one. Since we have not swapped them all, that means that they are diastereomers. Now, constitutional isomers would be if we put, say, the chlorine down here. The same molecule would be, again, it would be, say, both of these are, so you would have to not have to flip them around, things like that. So enantiomers means all of them, right? So if you have 10 chiral centers, in order for them to be enantiomers, they'd have to have all of them flipped. If it's less than all of them, then they're diastereomers, but it'd be 1 or 8. Okay. So for here, so how many possible diastereomers there are? 2, 4 diberyllyl and pentane. Okay, so the way this works is, again, it's 2 to the n, where this is the number of chiral centers. But you have to be careful of meso compounds. So go ahead and just draw this out. So this is 1, 2, 3, 4, 5, right? So let's put your dots. Don't worry about wedges and dashes right now. So 1, 2, so it's bromine. Okay. And then this is 4, so it's bromine. So notice how there is so here's your chiral center here, here's your chiral center there. But there is a nice plane of symmetry that could happen there. So what that means is that you probably will have a meso situation. And so you're not going to have, it's going to be less than this, right? Because you would think it'd be 2 to the 2, which would be 4, but because you're going to have that possibility of meso, it's not going to be the maximum amount. So you can knock those numbers down, stuff like that. So in this case, you're going to have, the answer is actually 3, right? Because if you had this one, and these, and this, it's the same molecule, you can just flip it over. So these are the same, so it knocks down the total possible. This is the absolute most, the highest number you can get, but that number gets knocked down with meso. So I would suggest going ahead and just drawing this molecule out quickly and looking to see if there's a possibility for plane of symmetry, because lots of times there will be. To trick you up here. So for this one, so the chemical ratios between 2s, 3r, chlorohexane, and this one here. This one is actually very easy to look at. Okay, you don't have to draw anything out. You don't have to do any of this stuff. Because what you do is you say, okay, again, notice how we'd have to switch them all the wedges and dashes, in order to be an enantiomer. We don't switch them to the big diastereomers. Again, when we switch a wedge and dash, what do? We convert it from an R to an S, or an S to an R. And so here, the 2's, notice how, again, these are the same. But here, they've been switched. So that means we kept this wedge and dash the same, but we've switched this one. We have not switched them all, so again, they're diastereomers. So if you wanted to have the enantiomers, right, the enantiomer for this first one, right, would be, what is it, 2R, 3S. Okay? You don't have to draw them out. You don't have to, figure it out, any of that stuff. You just look at what this is, and when you switch a wedge and dash, you flip from an R to an S, and so it's actually a pretty quick answer for this. Okay, so which one is optically active? So that means it has a chiral center to it that's not meso. Okay, so you have to be careful, because if it's meso, then it's not. It has chiral centers, but it's not considered optically active. Okay, so for here, right, this is definitely not meso, because there's no possibility for a plane of symmetry, because you have 2 different groups. Now, if they were both methyls or both OHs, you could have that. It's a little bit crazy. So for here, right, we've got H, right? So we have H, OH, so we have CH2, CH2, right? So that's going to be the same. So what do? We go out one right. So we have a CH versus a CH2. And that means this side is different than that side. So 1, 2, 3, 4 different things. We have a chiral center. So this is going to be octavely active. Okay, so for here, right, we have chlorine, hydrogen, right, hanging off, because this is probably, right, this is CH2, CH2, CH3, CH3, right? These groups can't be chiral, right, because they have multiple hydrogens on them. So when we radiate from here to see if this could potentially be one, we have CH2, CH2. Those are the same, so we have to go out one more. CH3, CH3, again, it's the same, but we're at the end of our chain, so this is not a chiral molecule, right, so it can't be octavely. Okay, so for here, right, we've got an ethyl group here, a set of lone pairs, a hydrogen, and then an isopropyl group. Hey, we've got 4 molecules. This should be octavely active. Caveat here: nitrogens. Okay, it all comes down to this set of lone pairs, and now the nitrogen's a little quirky in the fact that this lone pair can actually tunnel through the nitrogen and actually tunnel through to go down here, and what that does is it flips it to the other stereoisomer. So you get, unless you're doing this completely cryogenically, this thing is actually going to be flipping back and forth between R and S. So like that. So yeah, this does have 4 things, but it's that quirky little nitrogen sort of exception. That if the chiral center is on a nitrogen like this with a set of lone pairs, now if it's quaternary, right? So if let's say you have another group here, so it's charged, then no problem, you've got yourself a chiral center. But if you've got a set of lone pairs and a nitrogen, it's never going to be stable enough to stay put enough to be octavely active. So it's not going to be this one. However, if you have something like this, right, a sulfur, the other ones typically it's going to be things like sulfur and phosphorus. Those are actually stable enough that with the lone pairs. Okay, so again, you've got an ethyl, you have an oxygen, you have a chlorine, and you have a set of lone pairs. That's fine for 4 different things. Sulfur is going to be stable, right? So this is going to also be octavely active because there's a nice chiral center right there. So you've got these 2. Okay, so for this one here, so when you're create a product with a meso configuration, again, you're looking for that plane of symmetry. So if you look here, right, so you've got, you're doing hydrogenation, so instead of H2, you're doing D2. And so you would end up with this, DD. So again, remember this is a synaddition, right, because the hydrogen's going to come in and it's going to put it, the hydrogen will be sticking up, the molecule's going to come down, grab the 2 on the same side, and get pulled away. Okay, so this one's going to give a meso problem. This one here, remember this is when you're adding things like chlorine or bromine, things like that. That's an anti-addition, right? Anti-addition, right? So that's not going to happen. Okay. Here, right? So this is oxymercuration. So this will also be sometimes mercury acetate. Remember, it goes on the high. You add an OH across that side, and the fact that you're adding an OH, this methyl group, but you're putting it here, right? So you end up with OH CH3, right? And you can say, oh well, maybe there's a plane of symmetry going right there, but again, if you look on this side, there's not a chiral center here, right? Because these 2 sides are the same, so it can't be this one. So for this one again, so for the osmium tetroxide, NMO is just a recycling, so you can use catalytic in the osmium tetroxide. Remember, the osmium comes down and adds on the same side, so this is a synaddition. So you would end up with this product. Nice point of symmetry. So it ends up being those 2. So that's what you're looking for when you're trying to make it meso compounds. Lots of times you're going to need to look for syn and anti, particularly if it's on a ring. If it's not, you can become much hairier because you can get free rotation. Okay, so for the molecule here, for the enantiomer of this molecule. So the first thing you could do, okay, is find the RS on this one, and then what you're looking for is the enantiomer is trying to figure out which one is the opposite. Okay. The other thing that you can do is just look to see if there's been anything anything switched. Now rotate's fine. So if you rotate around one of these bonds, that's okay. So that doesn't change the configuration. But if you have a couple things fixed and you've switched the other two, then it's the enantiomer. Okay. So notice how all of these have this this ethyl with the thiol on here fixed into the back. Okay. So for here you've got methyl oxygen hydrogen, right? So methyl oxygen hydrogen, right? So it's kind of going around like that. It's still going around like that. So methyl oxygen hydrogen, again, it's going right around like that. But here it's going back this way. So methyl oxygen hydrogen. Okay, so notice how this one is still pointing up, this one's still pointing back, but these two have been flipped. Okay, so that means that this one must be the enantiomer. Okay, so we can go here. We didn't have to figure out RNS. We didn't have to do any of that sort of stuff. So just keep going around, see if you can find some that are fixed. And going. Brute force way would just be coming in and doing R and S and figuring out, this is R, 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 R. S. I don't know what it is off the top of my head. But one nice thing is that once you set the priority groups here, you know what the other priority groups are going to be. So you know it's going to be 1, 2, 3, 4. So it should be fairly straightforward to get your to figure out what R and S is. So after you figure it out the first time. Okay, so last one. So how many chiral centers are present? So when you do this, the thing to do is to go in and, again, draw the hydrogens. Okay? Because if there's multiple hydrogens, then it can't be a chiral center. Right? So for here, right, so there's one bond shown, so this is CH3. Here, 3 bonds shown, so there's an H here. Okay? Here, you don't even have to worry about it, because on double bonds, you can only have 3 things on there, so you don't have to worry about this one and this one. Okay? Same with these guys. Right? Double bond. Right? So this is a CH2, so you don't have to worry about that. Here, right? 1, 2, 3, so there's a hydrogen there. Here, 1, 2, 1, 2, 3. So again, there's a hydrogen here. Right. So here's CH2, CH2. Right. Don't have to worry about the oxygens, so we don't have to worry about those. Okay. So for here, so for this chiral center, right, we have a CH3, a double bond, carbon-carbon double bond, an H, and this CH bond here. Right. So there's going to be a chiral center there. Here, oxygen, CH, CH, but this one's coming off of, has a ketone hanging off of it, and a hydrogen, right? So there. And for this one, right, same thing, right? We've got a ketone on this side, you got CH2 and H, and then the CH, right? So there's one here. So if you knock out a whole bunch of these that aren't there, then you can figure out pretty quickly, because you still have to kind of figure this, take a quick look, right? Because if this was like CH3, CH3, then you would knock that out. But so for here, looking at the hydrogens is a really quick way of